Okay, so now we're going to talk about the normal force. And the word normal, that comes from mathematics. Normal, it means perpendicular in math. It's equivalent to the word perpendicular. I wish we would use that in geometry. Perpendicular, so the normal means this. So it's any time that anything is perpendicular to something. And so when we talk about a normal force, we're talking about a perpendicular force. And what the normal force is, it's a reaction, reaction to pushing on a surface. A surface. So you could imagine, let's start with a spring. So imagine there's a spring, right? And if I place a box on it, a box is going to push down, and when it pushes down, the spring is going to push back, right? So it's going to push straight up to hold it up. And then if I put a really, really heavy mass, well, then it kind of still pushes up. It pushes against it. Well, think, what if I put a meter stick, supported across two blocks, and I put a heavy mass? That surface is going to bend a little bit, but it's going to push up. It's pushing against the push down. It's a reaction, and it's perpendicular, just like these are. Yeah? And so when we look at a solid surface, what we have inside of it was we have a bunch of atoms. This is not to scale. These are not how big atoms really are. And these atoms are held together with little forces. They act like little springs. They go sideways too, in all directions. They're all connected. But you can imagine that they're like little springs. So when you put a big, heavy object on it, these springs, they compress just a little bit, so they push back. You have all these little pushbacks from all the atoms. And so that results in one big pushback that we call the normal force. We call it the normal because it's perpendicular to the surface. Now, what happens when it's at an angle? Well, it's the same thing. We have these atoms and they have little springs in them. But now the object, even though you think it's like pushing this way, it's actually pushing on the surface, and it's the spring action that's resulting with a pushback. And so we get a normal that's like this. It's perpendicular. It's always perpendicular. That's the definition. Normal is perpendicular. Okay. So what does this all mean? It comes up, we have to use it quite a bit, especially when we get to friction. Friction relies on the normal force. So we got to be able to determine what the normal force is for different situations. And the easiest case is just when we have an object sitting on a horizontal surface. So thinking about the forces acting on this, we have the force of gravity, or the weight, acting down. And that weight is going to be mg. So we can go ahead and write that. Now the surface pushes back. It pushes back, so we get a normal force from the bottom that's pushing up like this. That's perpendicular. And if the object's not moving, which in this case it's not, it's just sitting still, well, then I know that the net force is equal to 0 by Newton's first law. So I know that the normal plus weight is equal to 0. So I know the normal is the opposite of the weight. So in this case, normal would be equal to mg. G is negative, so I would get a negative, negative, so it's positive. And that makes sense, it's pointed up. Here's the thing, this is a special case. This is only for horizontal surfaces. Horizontal surfaces. With no additional with no additional forces. So I don't want you skipping straight to this and always say, well, what's normal? Oh, it's mg. It's mg. No, it's not. That's not true. Suppose that I have this box sitting here with mass m, and I push down on it. So you're pushing on it. You're pushing on the box. Let's say you're pushing with a force of F. So now you have some other forces going on here. You're going to have Sorry, I was trying to change my pen color. You're going to have the weight pushing down. That's mg. But now you're also pushing down. So we have this added force right here. So we have some more force. We have F. And then the surface pushes back. It reacts to all the push down. And that's the normal. And that's perpendicular. So again, it's not moving. So I know the net force is equal to 0. And now I have to add them up. So I have the normal plus this force that you're pushing plus the weight equal to 0. So I see that the normal is equal to negative F minus W, or the sum of F and W, just in the other direction. All right? So I can see that it's not always mg. And it's really not mg when we start talking about inclined planes. Let me get a new page open real quick. So suppose we had an inclined plane. It's inclined at some angle theta. And there's a box sitting on it. All right. So it's just sitting there. Well, we know that there's some weight, and weight always points straight down. So this is my weight, and weight's equal to mg. Okay, and that's it. But since this is pushing on it, the normal is pushing back. So the normal is pushing up like this, normal. And now we have to slant our axes. You know how we do that. So we can see that the normal is acting in the y direction in this case. Weight is at an angle, so we have to draw it in and we have to get these components. So remember, this is weight in the x, this is weight in the y. So now I know that in the y direction, it's the same in the x. There's got to be some friction here holding it up. Force of friction. But all I care about is the normal. So the sum of the forces in the y direction is equal to 0. So adding those up, I see that the normal plus the weight in the y direction, everything that's acting this way, is equal to 0. So the normal is equal to the opposite direction of the weight in the y direction. And now we could do our trig. So if I put the angle right there where it goes, then it's next to, so it's going to be the weight times cosine theta. And weight is always mg. So mg cosine theta. G is negative, so this all becomes positive. Okay? So you got to be careful. Normal is not always mg. We have to deal with whatever we have, and we just add them all up. It can increase, decrease. Let's do one where it decreases. So let's suppose that we have an object sitting on a scale. And let's say the object weighs, I don't know, 300 newtons. And there's a rope attached, and we're pulling upward. It's a rope, so we say tension. We're pulling upward with about 100 newtons of force. What's the normal? All right, so we have some weight acting down, and then we have the normal. That's the scale pushing up. But then we also have tension. You know, I already drew it. It's right here. So what we have to do is the sum of the forces in the y direction is 0. So we have the normal plus tension plus weight is equal to 0. Now remember, weight is facing down, so that's a negative. So we're going to get the normal equals negative tension minus weight. Or the normal is going to be negative 100 plus 300. Or 300 minus 100. So the normal is going to be 200 newtons. And that makes sense, right? We have 300 pushing down. We have 100 up, so we need another 200. So the reading on the scale would actually be 200 newtons. And again, it makes sense. The scale doesn't read the weight, it reads the normal force. All right, so go ahead and go practice.